All right, guys, so before we get started, are there any questions of the homework assignments? Questions over the homework problems? One thing I will say with logarithms and some functions, natural logs 2, natural log of 7 plus 2, we would not type this in as natural log, parentheses, 7 plus 2. Without parentheses written, it's understood, for whatever reason, that this is actually natural log of 7 and then add 2 to it. I dislike this form because it's sometimes confusing. Unless we know that, we're going to want to do parentheses 7 plus 2 and take the natural log of 9, but it's actually the natural log of 7. Once we get that decimal approximation, then we add 2 to it. Thank you. Now, first thing we're talking about today is using inverse properties with logarithms. And what's interesting, because they are inverses, that log base b of b to the x, when this b and the base are the same, this will simplify, leaving us with just the exponent left over. And b to the log base b of x is just x. They undo each other. They simplify each other down. And the reason this is helpful is if we look at this first one, a, 10 to the log of 4. Now, even though it's not written, it's understood that when we just have a log without the base written, its base is 10. And according to this inverse property, if the base of the logarithm and the base of what we're putting this to, 10 to the log of 10, those base and the base of the log are the same, we'll simplify out, leaving us with what's inside the logarithm, which is 4. So 10 to the log of 4, 10 log of 4 is just 4. They simplify each other out. And if we type this into the calculator, 10 to the log of 4, it will also tell us that it is indeed 4. They simplify each other out. And this becomes very helpful, especially if we do not have a number inside the log. So if I had changed it and said 2 or just x, now this is saying that 10 to the log of x would also just be x. As if, like the one they had here, it's just a number, we can plug it in and it'll tell us this. Here, I can't plug in 10 log of x into the calculator. X is a variable. It can represent any number. But 10 to the log of 4, it verifies, it does tell us that it is indeed 4, and it simplifies out. Questions on A? Let's look at B. Log base 5 of 25 to the x. Now, to be able to simplify this, it would be nice if this base and the number inside here, this 25, can be written as 5 to a power. Well, 5 to what power is 25? 2. Because 5 squared is 25. Now, I put that extra set of parentheses there to signify that 5 squared is 25, we replaced it. And it'd still be put to the x power. Questions on anything we've done so far? Now, it seems odd I would want to rewrite this and do this, but I want that base of the logarithm, which is 5, to match up to the base of what's inside the log. I want these to both be 5. Because according to this inverse property, log base b of b to the x is just x. It is that exponent. So if I can get that base and what's inside the logarithm to be the same, it will simplify out, or simplify to the exponent. Now we have one last step before we simplify, and the fact that powers of powers multiply. So really what we have here is log base 5 of 5 to the 2x. Because the base and what's inside the log are the same, they're both 5, it will simplify out, it will reduce, and give us the exponent, which is 2x. So log base 5 of 25 to the x reduces to 2x. Well, it reduced to log base 5 of 5 to the 2x, which reduces to 2x. Questions on either one of these here? And the whole goal of this is for us to be able to rewrite and simplify expressions down into a more or easier form we can use. And it's going to become more prominent, especially once we start solving. Ten to the log of 18, which is 18. Yep. Log base 4 of 16 to the x. Mm-hmm. 4 to the second to the x. Mm-hmm. Which we really can just say is what? Log base 4 of 4 to the 2x. Powers of powers multiply. 2 times x is 2x. Questions on this here? What would that reduce to? 2x. Mm-hmm. Because the base and what's inside of it are the same, it's going to reduce to 2x. Because, and as we're going to get into it eventually, especially tomorrow, what this is really tagging into is our power property with logarithms. That's really going to tell us that we can move an exponent to the front. We can move out in front of it, it's being multiplied by it. And log base 4 of 4 is 1. So 2x times 1 is just 2x. And we'll see that in more detail tomorrow. But questions on either one of these here? Number 13, 8 to the log base 8 of x. Well, these are the same, so this would reduce to x, because it reduces what's inside the log. When we have a number to a power of a log, whose base is the same as what that base is, we just have whatever's inside the log left over. They reduce out. Number 14, log base 7 of 7 to the negative 3x. This would be negative 3x. Mm-hmm. Because it's just going to be whatever that exponent is. Since the base and what's inside it are the same, that exponent is what we have. Mm-hmm. Because logarithms and exponentials are inverses of each other, they undo one another. They undo each other. Now, unfortunately, number 15, log base 2 of 64 to the x is not going to be x. Because if this is going to simplify nicely, I need to be able to rewrite 64 as 2 to a power. 6 times 2 to the 6th is indeed 64. Powers of powers multiply. So now we have log base 2 of 2 to the 6x. So this is going to reduce to 6x. All right, we got one more of these here in this set of 4. We have e to the natural log of 20. What would this be? It is. It's going to be 20. Because what is the base of natural logs? It's understood to be e. So even though it's not written here, it is e, and that base and the base of the logarithm are the same, so they would reduce out, giving us 20. Another nice thing with this one here, is there any variables in this expression here, e to the natural log of 20? No, we'd be tempted to say e, but e is a number, it's an irrational number. Since there are no variables, we can go second e to the ln of 20, and the calculator will indeed tell us that it is 20. Questions on this here? Now again, I said that these two are inverses, so one of the functions inverse, so an exponential's inverse, will be a logarithmic, or a logarithm. And a logarithm's inverse will be an exponential. Now, to find inverses, you've done this before, it's been a while, but there's several main steps. First step is to rewrite f of x as y. Rewrite f of x as y. A has f of x, B does not. If it doesn't have f of x, g of x, h of x, z of x does not have our function notation, it already has y equals, we don't have to do this step. So y equals 6 to the x. Step 2, we're going to switch x and y. Because what an inverse is, so a function takes x values, the domain, and what we call it mapping to the range. It maps x to y. It takes an x value that we plug in, and the function takes it to its corresponding y value. It takes an input to an output, an x value to a y value. Yes? Inverse takes that given y value back to the x value. So if we had this function here, we plug 0 into x, the y value is 1. So according to this function, it maps 0 to 1. 0, 1 is our point. Inverse goes the other direction. It takes the input of 1 and maps it back to 0. So they're switching that input-output. That's why we switch x and y, because it takes it the other direction. So for us here, we still have the 6, but the y is going to become x, and the x is going to become y. They flip. Now we're going to solve it for y. Now this here, all we're going to do is do what we did yesterday. We're going to rewrite it from an exponential to a logarithmic. So our rewriting as a logarithm was our log base b of, let's see here, x equals y, if and only if b to the y equals x. And depending on how it was written on the notes, really doesn't make a big difference, but that switch is still the same. So here we are given it's given to us in this b to the y equals x form. So to rewrite it as a logarithm, this would be log base what? 6 of x equals y. we did our switch. It's all is y by itself. Yeah. If it wasn't, we would add or subtract. We would still solve, but we do want to rewrite it in this form. Honestly, rewrite y as f to the negative 1 of x. And that's our inverse. Now the nice thing about inverses, their graphs are reflected across the line y equals x. So the negative 1 just says inverse. So it's telling us, so f to the negative 1 of x is f inverse of x. So it's telling us that the f of x function, 6 to the x, and f inverse of x are inverses of each other. That 1 is the inverse. And if we looked at the graph of these two, clear these two out, 6 to the x and log base 6 of x, we just said were inverses. And if they are, they will reflect across this line y equals x, the parent function of all lines. And they do. We can see there is this symmetry across this line, so those two functions are inverses. This is kind of nice to know, especially on the ACT, if it asks you to determine if two functions are inverses, or find the inverse. We can graph the two functions or graph the functions and see which one reflects across this line. If it does, it is an inverse. If it doesn't, it's not. Questions on how we found this inverse here? We're going to do more. Let's look at B. Y equals the natural log of x plus 3. Step 1 is rewrite f of x as y. It didn't start out as f of x. So we're not going to do step 1. We also won't do step 4. We'll just write it as y equals. Now the first thing we want to do is switch x and y. So y is going to become x is going to become y. Everything else stays the same. We just flip the x and y. We're not changing anything about the function. We're just saying the input is becoming the output, and the output is becoming the input. Now we need to rewrite this. We need to start solving for y. And the first main step I would do is use our switch with natural logs. So the natural log of x equals y if and only if e to the y equals x. So here when we do this switch, we will have e as the base. What's going to go up in that exponent? Almost. Because we put up in the exponent, because it's tempting to say y, because y is over here, yes? But what it's equal to, what the natural log is equal to, gets put up in the exponent. So here what it's equal to is not y, but... So we rewrite x equals natural log of y plus 3 as an exponential. We do have that base e. It's put to what the natural log is equal to. So x is equal to what's inside the log, which is y plus 3. Is y by itself. Now it has plus 3 with it, yes? So if I want to get rid of that plus 3, we would. Minus 3. Telling us y is equal to e to the x minus It wouldn't go up into the exponent. It would just be out to the side. Questions on this here? Yes. Second ln e to the x minus 3. This is our function here. Now, if we notice with this one here, it does go below that y equals x, the line that it's supposed to reflect across it. And that's fine, because our inverse, or the original function, because that was the inverse, was the natural log of x plus 3. And we do see that we have this inverse. Now, the natural log does not look like it continues down past that point. It does, it's just infinitesimally small next to this line, this vertical line of x equals negative 3. Because what's inside the log cannot be negative. So it's not going to be smaller than negative 3. But we can see that these do reflect across that line. Yes? So that means they are indeed inverses. Questions on how we did either one of these here? We ready for the next one? Okay. F of x equals 11 to the x power. First thing we want to do is rewrite f of x as y. Y equals 11 to the x. Then we want to switch x and y. So we have x equals 11 to the y. Questions on this here? Now, for the most part, I think we're getting down, switching between logarithmic and exponential form, yes? Because we look at this here, we know that we're going to have log to the base 11 of x equals y, yes? What did we just say about logs in their base and what's inside? If the base and what's inside the log are the same, they simplify. They reduce to whatever the exponent is, yes? So I actually could, and this we'll start doing especially with solving, can apply log base 11 to both sides. Because if I do it to the left-hand side, log base 11 of 11 to the y. What would this be? It would just be y, yes? But I can't do something to one side. We got to do it to both sides. Now, the left-hand side, log base 11 of x, 11 and x could be the same. They're not necessarily the same, because there's one case where they do. But we can't just straight simplify it. It just tells me that log base 11 of x is equal to y. Well, wait, that's exactly what we were doing with the switching between one and the other, yes? This is what we were doing. We just weren't explicitly saying this is what we were doing. Because we can apply log base 11 to both sides. Log base 11 of x doesn't simplify, it's just that itself. But log base 11 of 11 to the y reduces to y. Tell me y equals log base 11 of x. And because we started with function notation, we're going to end it with function notation. F inverse of x is equal to log base 11 of x. Questions on how we did A before we look at B? Y equals the natural log of x plus 6. Don't have f of x, so I don't have to rewrite f of x as y. So we can go to step 2, which is rewriting or switching x and y. Now, if we're starting off in logarithmic, we said just a minute ago when we have a base to a log, I'll rewrite it out, we had b to the log base b of x. When this here and this here are the same, it reduces to what's inside the log. So b to the log base b, if I have that, if the base of the log and the base of what we're putting the log to are the same, they reduce out. What is the base of this natural log? E. Base of all natural logs is e. So here, if I put e, I put this natural log to the base of e to the natural log of e, what is the right-hand side reduced to? Because this e and natural log will simplify each other out. But if I put one side to the base of e, I've got to do it to the other side as well. So it is also possible to put both sides to a base, essentially put them up into the exponents, apply that base to both sides. And here, applying base e to both sides, left-hand side becomes e to the x, because that's not going to reduce. But the right-hand side, e to the natural log of y plus 6, the e and natural log reduce out. They undo each other, leaving us with y plus 6. Which, again, that's our switching method for natural logs. Questions on this here? Is y by itself? No, so we need to what? Subtract 6. Telling me y is equal to and that would also work with our logs. We're just trying to get it by itself. And this here, this step that we're doing is going to be critical and essential for solving when we start trying to solve these. Because if I can get that log by itself, I can put both sides to the base of that log to get it to reduce. Or if I have an exponential, I can apply the log of that base to both sides to get it to simplify. Y equals 4 to the x. So the first thing we're going to want to do is what? Switch the x and the y. And when we do that, we get x is equal to 4 to the y. Now at this point here, you can do the switching method, or we can apply a log to both sides. And if I'm going to apply a log to both sides, I'm going to apply a log that's going to make that base of the right-hand side be the same as the base of the log. So I'm going to apply log base 4. Because on the left-hand side, log base 4 of x is just, well, log base 4 of x. It doesn't simplify. But on the right-hand side, we have log base 4 of 4 to the y. That log base 4 of 4 will reduce to just y. We can leave it as that there if you want to switch it. Y equals log base 4 of x, you can as well. But that is it. Questions on number 17? We good with those here. Since it didn't start with, so the reason we wouldn't put the f inverse of x, f to the negative 1 of x, is because it didn't start in function notation. Yeah, if it gives me function notation to start, I want to finish in function notation. Didn't give it to me to start, I'm not going to finish with it. y is equal to the natural log of x minus 5. What do we need to do first? Switch the x and y. Then yes. Because after we switch the x and y, we need to get that y by itself. We need to get it out of the logarithm. This is what we're really trying to do. And yes, we would use that base of e. Because e to the natural log of y minus 5, the e in the natural log will simplify out, leaving us with y minus 5. However, e to the x is going to be just e to the x. Is y by itself? Well, no. What do we need to do? Plus 5. Telling us y equals, and since it didn't start in function notation, we're not going to end in function notation. So that's it. Questions on this here? What do I want to do? 4x. Why not? Give me a number between 1 and 10. 10. 10. I want to do one more. You can write this down if you want. You can watch it also. I want to do one where we have a little bit more with our logarithms. We won't necessarily get to this complexity a whole lot, but I want to show you that this looks like it should be more, not a whole lot more than what we were doing. Because the first main step still holds true. If it gave us f of x, we would rewrite it as y. They didn't, so we don't have to do that. Second main step still holds true. We're going to switch x and y. Now I'm going to write it underneath it because I definitely did not give myself enough room to apply log, especially between the 10 and that equal sign. But I can apply a log to both sides. And what would the base of that log be? Because what is the base of our number that we were given? 10, so the base of that log needs to be 10. We can write it in, but luckily for us, it's understood. To be 10. Because we'd have log of x equals log base 10 of 3y minus 7. Now on the right-hand side, log of 10 to the 3y minus 7, well, the base and what's inside are the same. Because the base is 10, we did not have to write it. It's just telling me the right-hand side becomes 3y minus 7. The left-hand side is going to be log of x. Now we just need to solve for y, because y is not by itself. 3y minus 7, well, the first thing we can do is what? Add 7. Telling us that we have log of x plus 7 and divide by 3. Because the 3y divided by 3 is going to be y equals and that's it. It did add more steps. But would we say that the difficulty of this problem is any harder than what we were doing? No, it's just more steps. We're having to do more steps, a longer process. But really, the adding here and dividing by 3, we've done this before. We haven't done it with a log. We haven't had log stuck in the middle of the problem that we're having to work with. But we have done these solving steps before. Questions on this here? But that's it. That's it, especially with these inverses and how we get to it. And especially when we start solving, this is really what it's going to start looking like, is doing these steps here. And one of the biggest things I started a few years back, especially with solving, getting to this here, it's not going to be log of x. We're actually going to have a number in there. So log of 5 plus 7 over 3. I will take that. I do want you to plug it in, get an answer, but I do take that. If you've got that, but the answer approximation is wrong, I'm not counting off, especially on the test. Because I'm testing on your ability to solve the problem. You got here, you solved it. If from here to the decimal approximation is what you got wrong, that's not your ability to solve it, that's ability to plug it into a calculator. Not what I'm judging on the test. Test is, can you solve it? But that is it for 6.32.